Commercial roads for neuromorphic technologies up to 2025. Alright, today we are diving into a really cool revolutionary type of computing, which is inspired by the most efficient processor we know of, the human brain. It's called neuromorphic technology, and for decades it's promised the incredible power savings, but it's always been just over the horizon. Well, now a key breakthrough is finally clearing the road for it to go mainstream, and we are going to break down exactly how they are pulling it off. So let's just start with this big idea. Think about it. Your brain doesn't just crunch numbers one by one like a calculator, right? It processes a ton of information all at once in parallel, reacting to new things as they happen. And it does it with incredible efficiency. So, what if our computers could do the same? What would that even look like? Okay, so to really get what's going on, you got to meet the three main players in the world of computing today. You all know the CPU is the reliable workhorse chugging along step by step. Then you've got the GPU, the powerhouse of AI that handles huge chunks of data all at once. And now there's this newcomer, the neuromorphic chip. It thinks in a totally different way. It's event-based, which means it only acts when new information comes in, kind of like how neurons fire in your brain. In that style, that's its secret to being super efficient. Now to predict where neuromorphic tech is going, we first have to look backwards at the incredible success story of its cousin, the GPU, because the path it took from being just a niche product to becoming the king of AI. Well, it holds the exact lesson that neuromorphic computing desperately needed to learn. GPUs weren't always the AI superstars. They got their start just making video games look pretty. For years, all the amazing parallel processing power was basically locked away, and only graphics specialists could really use it. But then in 2006, NVIDIA did something absolutely brilliant. They released a kind of software key that unlocked all that power for everybody. So what was this key? Well, it's called an API, an application programming interface. For NVIDIA, it was called CUDA, and you can think of it like a translator. It let any programmer, not just the graphics experts, tell the GPU what to do using programming languages they already knew. It made something incredibly complex feel simple and accessible. And this is the part you really have to remember. The huge breakthrough wasn't just better hardware, it was making that hardware easy to use. The real killer app for the GPU wasn't a game or a program. It was the programming model that CUDA made possible. That's what allowed the entire AI community to unleash its full potential, and that led directly to the AI revolution we're living through today. This is the heart of our story. Okay, so now let's turn to our main character, neuromorphic chips. With their brain-like efficiency, they've been the dream for engineers for decades. I mean, huge companies like IBM and Qualcomm have poured money into them, but for all that promise, they've always had this critical fatal flaw. This quote from the source article for this explainer just says it all. For decades, these chips were just incredibly, almost impossibly difficult to program. You couldn't just sit down and write code. You basically needed a PhD in computer science and another one in neuroscience just to get them to do anything useful. Just look at the struggle here. Programming these chips was the tangled, complex manual process. It was less like writing code and more like performing brain surgery. You had to personally design these neural networks, requiring this deep knowledge of the brain itself. They were missing their version of CUDA, that simple, powerful way for developers to just build things. And this difficulty was the single biggest thing holding them back. But that's all changing. Finally, the neuromorphic field has found its secret weapon. It has found its CUDA moment, the breakthrough that makes this brain-inspired hardware accessible to everyone. And what's so wild is where the solution came from. It wasn't some brand new exotic invention. Instead, the answer was to build a bridge from the world of deep learning over to neuromorphic computing. They decided to borrow the powerful training techniques from mainstream AI, the very same methods that engineers already know and use every single day with GPUs. And this new recipe is a total game changer. Developers can now just use familiar tools they already love, like PyTorch, to set up tasks. Then, using this clever technique called surrogate gradients, they can automatically train a brain-line spiking neural network, just as if it were a standard AI model. All of a sudden, programming a brain chip is fast, convenient, and open to this huge global community of developers. Okay, so what's the big payoff for all this? Well, how about a number like this one? With that massive programming barrier gone, we can finally unlock the absolutely incredible efficiency of neuromorphic hardware on the right kind of tasks, like processing real-time sensor data. The power savings can be up to 1,700 times better than other specialized low-power chips. That's not a small improvement, that's a whole new world. Let's make this real. Think about an always-on device like your phone or smart speaker listening for a weak word like "Hey Siri." As you can see on this chart, a normal CPU or even a mobile GPU uses a pretty decent chunk of power, but the neuromorphic chip, you can barely even see its bar. The power savings aren't just incremental, they are truly fundamentally game-changing. It's not even a close competition. So, with the massive programming problem finally solved, where is this technology actually going to show up? Where are you going to meet it in your day-to-day life? Now, you might think these super efficient chips are headed for the giant data centers that power cloud AI, but you'd be wrong. Their killer advantage is at the complete opposite end of the spectrum. The massive, growing market for tiny battery-powered smart devices. This is the world of tiny ML, AI that runs at the edge right on the device itself, no internet connection needed. And this right here is what that future looks like in practice. Imagine a smartwatch that can constantly monitor your heart for problems and still have a battery that lasts for weeks, not just a couple of days. Or earbuds that are always listening for your command, but don't drain their tiny battery. This tech enables a whole new class of devices that are smarter, last way longer, and are more private, because all the thinking happens right there on the chip. So let's just bring it all home. The key takeaway is this: just like with the GPU, the neuromorphic revolution isn't about one specific product. The true killer app is the simple AI-driven programming model. That's the key that unlocks the potential for thousands of different applications. And it's what's making this brain-inspired technology commercially attractive for the very first time. This powerful combination of brain-inspired hardware and AI-inspired software leaves us with a really fascinating final thought. As technology becomes more and more integrated into our environment, in our ears, on our wrists, throughout our homes, maybe the most valuable kind of computation won't be the fastest, but the most efficient and aware. It really makes you wonder, will the best computer ultimately be the one that works the most like our own brain?